I mentioned that we are planning a project that's starting in 2 weeks. And the project is using the data set that we are going to use for this workshop today. And the data set, if you have taken a look at the data set, you know, but it contains records of collisions in Seattle. And to give you some background for this project, we all know that accidents are a serious problem. And according to the report that was released in 2015 by Washington State Department of Transportation, there were a little over 117,000 collisions that year, and about 34,000 cases of cell phone and texting citations were reported, and then 416,000 speeding citations were reported. Also, in that report, inattention or driving under the influence was cited as the most frequent contributing factor of the accident. So given this background, the main purpose of this project is to identify dangerous locations in the city and then make suggestions for improvements. And we're going to talk more about more specific goals for this project in a minute. And so if you are interested in this, joining this project, you can click on this link here. I don't know if you can see the meetup link, and then it will lead to the event page. So the project starts on July 8th, and it will go on for 4 weeks. And if you, like I said, we'll be using this data set for the project. So after this workshop, if you are interested, please join us for the project as well. Okay. Any questions so far before we get started on more content?
So it looks like there was a question about where the data comes from, and this data set, this smaller data set we're initially using for this example, comes from the City of Seattle's Department of Transportation. There is a version of that data set available in a CSV file that you downloaded. It's updated pretty regularly. There's also similar data available at the state level, but it's difficult to merge those data sets at the moment, and so that will be a task for the actual project team to tackle.
Any other questions before we move on? So I can't seem to see the chat window, so I'm relying on other people.
Well, if we want to move into section 2, obviously you can read it, and so I'm not going to read it to you, but why do you do this initial exploratory?
Sorry? I didn't interrupt, but do you want to share your screen so that you can?
Absolutely.
Yeah.
Let's do that.
I will stop sharing.
Okay. So it's helpful to know why you're analyzing the data set and what the end goal is when you start this initial exploration. So these are the project-specific goals that our team is considered important, but we are open to new goals, and we anticipate the goals changing over time as we engage in the analysis. But in light of these goals, to identify dangerous locations and look for predictors of accidents, that will be guiding the type of exploratory analysis we conduct going forward. I have run my notebook in entirety from top to bottom. I assume that everybody, since everybody's able to download the materials, has been able to at least run the import statement packages. If not, will you type the word help into the chat and somebody will help you. That's a blanket request for anything going forward. If a cell doesn't work for you or Jupyter workbook, the notebook is not working, just type in the word help, and we're monitoring that keyword. So hopefully somebody will be able to reach out to you directly in a private message and provide you with some assistance. So if you run these two cells like I have, you basically get the essentials, right? Most people are familiar with pandas, and pandas is the primary library that we use for the following analysis. The second cell depends what platform you are using to run this notebook. If you are using Jupyter Notebook Lab, you can disregard this cell because I think by default, the lab platform will allow you to see every single statement that gets executed. That it's not true if you're using the Jupyter Notebook. In that case, even if there are multiple statements that would produce an output, you only see the last output within the cell, unless you run this code in cell 2, which allows every single output statement to be printed at the bottom of the cell. This is a straightforward download of the CSV file. If you want to save the CSV file, this is just a handy way of figuring out where you are in your directory system and where you are going to save the file. The only thing that I would say about this that's kind of important is that when you ever are saving a CSV file, and this is geared towards the people who are new, for which we know that there are several people who are relatively new to pandas. So I'm trying to bridge the gap between the more expert folks and the newer folks. When you use the word index, the index parameter, and you set that to false, then you won't get the index, the numbers that would otherwise show up in your data frame printed to the CSV file. A little hint, it's very useful, a very important parameter. If you had already done that, or you wanted to read the CSV file that was already provided in the materials, then you could uncomment out these lines, make sure that this name is the correct name, and then you don't have to download the data from the website. So as you can tell, and this changes daily, depending on what data set you have. In this particular case, we have a little over 220,000 rows and 40 columns. The columns often are self-explanatory, but some of them are indecipherable as far as we can tell. Obviously, they mean something important. For instance, there are references to other reports, but it is not clear, based on the documentation that was provided on the website, what those reports actually refer back to. So we included this information about the original column names to kind of give you a little bit more information about what the columns are. For instance, you can see the report number and status. If you know what that is, please feel free to include that in the chat window. But this report obviously refers back to some report. We don't know what report that is or who generated it. There is a fair amount of missing data, as you can see from this cell. It looks like a lot of data is missing from certain cells. However, it's entirely possible that different individuals were responsible for inputting this data. It's not clear exactly how it was collected. For instance, if speeding is a simple Boolean variable, it's possible that if the individual wasn't speeding, they just left it blank as opposed to putting in a no or a 0. And so even though it looks like we have a total lack of data in the speeding column, that might not necessarily be the case. That's just a quick way to divide the numerical and the categorical features, because we will probably want to change the data types for columns going forward, but this is what was initially interpreted by pandas when we downloaded the data. The numeric variables in this data set are few and far between. There's not, unfortunately, a lot of numeric data. We can create various variables using the data to kind of transform them, like using count or binning variables. But as it sits right now, basically counts the number of serious injuries, the number of people involved in a collision. These are the numeric variables we have right now. I'm not going to go through all of the non-numeric variables, but we thought it was useful to kind of separate out external factors from the human factors, from the site-specific factors, because that might further influence our analysis going forward. However, there's a variety of other ways you could divide up the columns and think about what kind of data you have available. This is a very quick overview of cleaning at the data frame level before we move to individual columns. I don't know, I suppose most people have their idea for naming columns, various standards people use. I myself like to use lowercase. And so this is just an example of how to change all the column names into lowercase, became uppercase. If you like uppercase, then you don't need to run this cell. In a perfect world, I also like to see underscores that separate out various words, but I decided not to let that particular level of minutia influence our work so far. At the data frame level, you might think about dropping columns, you might think about dropping rows. You especially consider that when you have a large data set, and so it takes a lot of processing time to work through the data. This particular data set isn't that big, so it's less of a concern. And also at this point, it's not entirely clear, as I mentioned earlier, some of the columns might be useful going forward. Unless you have domain knowledge and you specifically know, for instance, what the report number column refers to. At this point, I am a little more cautious and I tend not to drop columns when I don't know what they're used for, but that is an individual decision. And of course, you can go forward and do that. For instance, object ID is literally just another index. And since we already have an index, you could drop that if you want. I used the keyword false in place. So this statement does not affect the data frame going forward. But if you change that to true, then you will drop the object ID column going forward, if that's what you want. But it's helpful to kind of go through and look at the individual data values and kind of get a sense of for instance here, this text is, I forget what that's called, where each word is capitalized, but not all caps. You might want to look at this and think, well, I want to make all of the text lowercase or all of the text uppercase, to kind of provide some consistency going forward. Even though this section is about dropping duplicate or unnecessary rows, I'm actually adding a couple columns, because even though you don't have to necessarily add these columns, you can definitely just do a sort based on the date or the year or the month from a date-time object. I find it easier to separate them out and just create additional columns. That'll be useful going forward when we do some visualizations. So when we look at the distribution of data by year, we see there's not a lot of data in 2003. In fact, I think there's like 5 whole incidents that occurred in 2003. So in terms of trying to delete rows to free up memory, in this case, not a big deal, but in the scheme of things, we might also want to include, delete 2020. Obviously, it's not a full year yet. If we're just looking at the distribution of incidents over time, we want to look at the progression. That's just a way to visualize it if you prefer to look at it as opposed to look at the information in a table. More often, visualizing the data is more helpful, at least the bigger your table is, the more helpful visualization is, right? In this cell, I did go and delete the 2003 data. So far, I've left the 2020 data, but you can definitely copy this and just change that to 2020. Sorry, I just realized, usually when you use the strip time function, I thought that usually produced a text value, but somehow when I used it as an int, that seemed to work. I didn't get an error message. Interesting. Anywho, I am all about changing the variable data types for a variety of reasons. One, memory issues. So categorical variables in pandas take up a lot less space than a float, for instance. It also changes how you can do aggregating functions like sum. So if you apply sum to your data frame, categorical variables will not be summed. So maybe that's a problem for you, maybe that's good. I provide an example of a way to change a bunch of different column variables. I'm sure that there is a much cleaner way to do it if you were so inclined, but I basically more or less use this function and I make changes as needed, and I basically reuse this. X and Y, in this case, are the longitude and latitude. I mix those up all the time to the point where I had to put a detailed explanation, not so much for you all, but for me, about which one was which. X is the longitude, Y is the latitude. Excellent. Sorry, I don't mean to make you sick. It doesn't look like it's scrolling that fast on mine, but I realize it might look like it's scrolling quite quickly on yours. I guess I've been talking for a little while and I have not seen anybody typing stuff into the chat. If people feel like I'm going too fast or you have questions about a piece of code, I am happy to stop and talk about the code in more detail. At this point, again, trying to balance between the experts and the newer folks. I'm not talking about what each single line does, but I'm happy to do that. Okay, back to changing variables. So I didn't change a lot of the variable data types, but I changed a few. Some of them more just for the demonstration, and some of them because I thought it was a really good idea. For instance, status, there's all values, or it's one unique value. And I don't know if you just saw that message, but apparently my internet connection is unstable. So if I drop out at some point, Niwako will take over seamlessly. But hopefully that won't happen. Especially since section 8 is where we are and Niwako was planning to handle section 8.
Yes. Are you there, Erin?
But I'm happy to start. So referring back to the earlier goals for the project as a whole, we decided to focus on just these. Dangerous locations, what kinds of locations tend to have more collisions than others. So that's goal 2, and examine the increase or decrease in the number of accidents over time, since we do have that handy date time data. As with every single decision as a data scientist or a data analyst, you know, how do you define something? Where do you determine what the criteria is? For instance, what is a dangerous location? Is it an accident that has a location that has 1,000 collisions? Is it 10,000 collisions? Where it's the cutoff? What's the appropriate cutoff? And so in this particular case, she looked at some of the numeric columns to kind of guide and give her an idea of where the cutoff, where the threshold should be. First, she was guided by which columns have the most data. If your column is missing a whole bunch of data, not particularly useful predictor for dangerousness.
Erin, did you want me to switch?
Going forward, as you could tell, there's not a whole lot of variability, but there are some occasional outliers. Like, for instance, on the person count, the number of people involved in a collision. Randomly, there is apparently Niwako.
Yes.
I think she'll sort out her technical difficulties. Apparently there was a collision that involved 93 people. You can hear Niwako.
Yes.
Thank you, I appreciate that. The she in that case was me. I will stop talking.
Okay, can everyone hear me? Or, oh, I think everyone can hear me. Okay, so maybe, thank you, Erin. I'm not sure what happened, but I can take it from here. And maybe I will share my screen. Hold on. Okay. Can everyone see my notebook? Okay, thank you. So I'm going to start. So for this section, I wanted to start answering some of the questions that might be helpful to achieve some of the goals. So Erin talked about several goals for the project, and I took 3 of them to organize this section. And I think Erin just went through here, maybe? Yes, so, well, first, I was thinking about how to define dangerousness. And as Erin mentioned, one way to define dangerousness is to look at the total number of accidents. Another way to define dangerousness is to look at the severity of accidents. So I'm starting with by looking at what these accidents looked like. That's why I'm looking at these columns. I'm naming these columns numeric columns because these are numeric columns. So the first, okay. So the first column is person count, how many people were involved in the accident. And the next one is how many pedestrians were involved. And the third one is how many cyclists were involved. And the fourth one is how many vehicles were involved. And this is how many injuries were involved and how many serious injuries were involved and how many people died in each accident. And so you can see that by just looking at the mean and these descriptive statistics, like the mean and standard deviation, minimum and maximum, we can see that there are some extreme values like 93 people involved in an accident or 78 injuries involved in an accident. So these might be outliers, and I'm going to come back to outliers in a minute, but if you, well, actually, let's talk a little bit of about outliers. What is an outlier? Would anyone like to give a general definition? How would you explain an outlier to someone?
Outlier is something that does not behave normally than what your data set performs. So it performs like an anomalous behavior. So you can term that as an outlier.
Okay, yeah, that's one way to describe it. So a value that doesn't look normal. Does anyone else have any other way to define it?
Doesn't follow the pattern?
Yeah, it doesn't follow a pattern. Yep, that's another way. Anyone else? Well, as you can see, there are many ways to define an outlier, and I just included this link to our Wikipedia page on outliers, and you can see that even in statistics and math, there are multiple definitions of outliers. So we're gonna, well, I'm gonna move on for now, but we're gonna come back to how to deal with outliers in a minute. So I'm breaking down some code here because I'm going to use this code a lot. So I just wanted to make sure that everyone knows what I did here. So here I'm trying to create a data frame by counting the cases per how many people were involved in each accident. So you can see that the most common number of people involved in an accident is 2. You can see that a little over 118,000 cases involve 2 people, followed by 3 people being in an accident. So that's how I'm creating a data frame. And then I'm creating a bar plot. And as you can see, a lot of the accidents involve 2 people. And then there's some outlier-like value, 93 people involved in an accident. And then to detect outliers, I'm using a Boxplot, and usually Boxplots are useful to identify outliers, but it doesn't look so useful here. And that's because the distribution is not well, far from normal. So, so I created a data frame and then a bar chart and then the bar plot, sorry, box plot. And I'm combining these 3 steps in this cell 30, and I'm also looping through the set of columns, numeric columns that I defined earlier, so that we can see the bar plot and the box plot next to each other for all of the columns. And so I'm setting up the area for the figures with the left side as the bar chart and the right side as the box plot. And you might notice that I'm assigning this under bar. This is just to prevent a long unnecessary text from printing. So you can see these bar plot and box plot, and this looks more like a box plot that we are used to seeing rather than this. So does anyone notice anything by looking at these charts? So I have some comments down there, but if anyone notices anything, feel free to share your thoughts.
Jennifer says that the major outlier in 2015 was, what was it, if you know?
Sorry, can you say that again? I couldn't hear you.
Sure, like Jenny said that there was a major outlier in 2015, and if you know, what was it?
Oh yeah, you mean that the accident that involved 93 people? I'm not sure that's what. Is that the one? I can't see the chat window, but.
The question only said 2015.
2015?
Mm-hmm.
I'm not sure if I can see the 2015.
Jennifer said there was another chart that it showed when she reviewed that earlier, and it had color.
Oh. I see. Erin, would you mind looking into that while I don't think. Erin, can you hear me?
Maybe that's ahead, so maybe you should just move on with the
Okay.
talk. Yeah.
All right.
It seems that most cyclists have are prone to more accident.
Cyclists?
So cyclists, this one currently, which is showing in your screen. So it seems that cycle count. So maybe cyclists are more likely to be in an accident.
Oh, I see. So this graph shows that most accident over 20, so I can see 200,000, sorry, accidents didn't involve cyclists.
So the big bar means that they weren't involved in the accident.
They were not involved in the accident. Yeah, that is correct. Anything else that anyone notices?
I noticed that because the number of fatalities 0 is huge, we cannot really see others perfectly. I was wondering if we eliminate 0 and get a better, then we can get more clear shot from the graph.
I see, yeah. So most cases didn't involve fatalities, which is good news. So if we go back to this numeric representation, you can see that actually 25 percentile through 75 percentile, they're all 0 fatalities. So my guess is that even, you're right, yeah, there are 5 fatalities as the max value. So yeah, yeah, if we get rid of the 0, the bar for 0, we might see more here. But in general, most accidents didn't involve fatalities. So to summarize, most common accidents involved 2 people and 2 vehicles and 0 pedestrians or 0 cyclists, 0 to 1 injuries. And then usually there was no death. And so let's talk about how you deal with outliers in your analysis. So I have some comments here, but ignoring these bullet points, if you want to share how you deal with outliers, feel free to share.
I think I sometimes have a hard time defining what is an outlier and whether I will be losing information or not if I remove it.
Mm-hmm.
But when I decide and I have to remove it, I just try to see. For instance, I think fatalities here, would you consider that outlier? Would you remove that? That's a question for everybody.
Yeah. Does anyone have any thoughts on how to deal with outliers in general, or how you might deal with this particular point?
For this, I'm wondering if you'd want to keep them, because since you're trying to see where the most dangerous accidents are, you're kind of looking for those anomalies.
Right, that's a good point. Yeah. Anything else? Well, like Erica said, it's important to think about whether or not you should deal with outliers or just leave them in the data set as they are. And also, you probably noticed that regardless of outliers, the distribution for each column here is skewed, and it's almost not like it's not distributed much. It's very limited in terms of variability in values. So this is one reason we explore data before we start doing analysis, to understand how much variability there is in a column. And there are yes, and like Ellen mentioned, sometimes we want to keep these outliers because that's what we are looking for. And if we get rid of them, we might not find any dangerous locations. So a few common ways to deal with outliers is to use transformation like log transformation, or you can also replace them with the median or the mean of the column. Okay, so let's get back to question 1, which was how to define dangerousness. So given that there isn't a lot of variability in these columns might not be very useful in finding or in identifying dangerous locations. So what else can we use to find dangerous locations? The other option is to look at the total number of accidents. So that's what the next question is asking about. So here I'm just counting the number of accidents per location. And you can see that this first row, Battery Street Tunnel northbound between Alaskan Way, Viaduct northbound, and Aurora Avenue. Some of you might know where that is the #1 location in terms of the total number of accidents, and there were 298 accidents. So these are the 7 locations with the highest total number of accidents. But we also need to keep in mind that accidents are more likely to happen where traffic is heavier. So when we do the analysis later on, we should keep that in mind. And if the data is available on how much traffic there is for each location, it would be a good idea to incorporate that in the project. So I just used the total number of incidents regardless of how severe the incident was. So in the next question, I'm asking which locations had the most severe incidents. To do that, I'm looking at this column called severity code. And originally it was just labeled 0, 1, 2, and 2B. But I read the dictionary that came with the data set and relabeled these numbers so that each category is more meaningful. So you can see that property damage only accidents are most common. And then the next common accidents involve injuries, and then serious injuries, and then fatality. So to identify locations with severe accidents, highest number of severe accidents, I'm only selecting locations that had accidents that resulted in fatality, serious injury, or injury. And I'm creating a data frame. And here you can see that Aurora Avenue North between North 117th Place and North 125th Street has the highest number, 126, followed by 6th Avenue and James Street. So I wanted to compare the 2 lists, so this list and the list that we created by just looking at the locations. And to do that, I sorted the locations alphabetically so that it's easier to compare. So this list is the list of locations with severe accidents. And this list down here is the locations with just any severity, accidents with any severity. And you can see that, for example, 6th Avenue and James Street appear on both lists. So do these two locations involving Aurora Avenue. You can see them on both lists. So when we compare them, we can see that 5 locations appear on both lists. 2 appear on just one list, and another 2 locations appear on this list. So it looks like there is an overlap between the number of locations with highest number of fatal accidents and locations with high number of severe accidents. One thing to keep in mind is that sometimes these locations might not be entered in the data set in a standardized way. So some people might abbreviate some names differently and not consistently with other people. So in that case, we might not be able to get the accurate ranking by looking at the location names. So using coordinates, so the column X and column Y might be a better way to identify locations. Does anyone have any questions so far? Okay. If not, I'm going to move on to the next goal, which is to identify what's related to accident, the risk factors for accidents. To do that, I'm going to look at external factors, human factors, and the characteristics of the collision site. Starting with external factors. So if you remember, well, Erin went over the chart quickly, but she had a bar chart for the lighting condition, and I'm going to go back to it. So does anyone notice anything about this graph? What do we see? So what can we say from this graph?
Somebody in the chat says that everything happens on daylight.
Yeah, it looks like daylight has the highest counts. So what does this mean? Does this mean that daylight is more dangerous?
Oh, it means that
We should get rid of the sun
more during day.
I'm sorry, can you say that again, Manas?
It means that people travel more during the day.
Yeah, exactly. So yeah, the more people travel, the more likely accidents are to happen. So that's something to keep in mind. And also you might notice that there are several subcategories for dark, like dark, no streetlights, dark, streetlights off, dark, unknown. So I wanted to combine these subcategories for dark, that which I'm doing in the next cell. Sorry to scroll so much. Yeah, so I'm relabeling these dark categories to just dark, and then I got a graph like this. And you can see that even if we combine all the dark categories, daylight is still much higher in frequency than the dark. So I wanted to have everyone do a simple exercise here. Given what we just saw here, I want you to create a graph like this, exactly like this, for the column weather. And I'll give you a few minutes to do that. So you can go ahead and start working on it. And when after a few minutes, I will ask you to share your code in the chat window. Okay. So if anyone is done with the chart, you can, if you want to, you can share your code in the chat window. Okay, thank you, Sophia.
And Rebecca.
Oh, thank you, Rebecca. Great.
Yep.
Yeah,
Those
let's
two
take,
seem really good.
yeah. So as you can see, there are multiple ways to do this, and I just did exactly what I did before. So you can see that I'm using the same code over and over. But whatever, oh, no worries, Jenny, no worries. Yeah. So whatever code you use, you should see a chart like this. And you should see that clear weather has the highest frequency. Right. And then, okay. So, in Seattle, yeah. Well, when the weather is nice in Seattle, everyone wants to go out, and maybe that's why more accidents happen. So far, just to summarize what we found so far, most incidents happen in the daylight and also in clear weather. So is a bad weather not a predictor of accident extent? accident then. So we don't know yet, right? It doesn't look like these weather or lightning condition are related to accidents right now. But if we do more or different types of analysis, we might find that these bad weather might actually be related to accidents. Okay, so moving on to human factors, we have these columns. So the first one is whether or not the driver was inattentive. The second one was whether or not they were under the influence. The third one is not really self-explanatory, but this means whether or not the pedestrian had the right of way. And the last one is whether or not the driver was speeding. And again, I'm doing the same thing. I'm creating data frame here by counting the values. And then I'm doing the same thing here so that assigning an underbar so that we don't get long text. And we get these pie charts. Does anyone have any comments on these pie charts? What do we see? Well, one thing that might be very obvious is that these two columns have a lot of missing values. For example, this one, 98% of the cases didn't have information about whether or not the pedestrian had the right of way, or 96% didn't have information about speeding. And something that's tricky about this column is that some of the, oh wait, do I see something? Yeah, or very few people are just speeding, yeah. Yep. So something tricky about this column is that some cases are marked 1 and some cases are marked Y. And then some cases are marked N, probably no, and then some cases are marked 0. So Erin's gonna go over this actually later. She's gonna combine these categories. So yeah, this pie chart suggests that most drivers were not under the influence, but it is a little bit tricky because of the way it's recorded. Okay, so I don't know if we have time for the next exercise. Well, let's do the exercise, and if we have to skip some of the topics, I'm happy to skip. So, oh, so I am hiding myself, but you probably see a list of columns that are characteristics of the collision site. named site characteristics. And those contain columns that describe conditions of the site where the accident happens. So looking at the bar graph, not the pie chart, but the bar graph that we created, I want you to create a bar graph for each of the columns. And you can do it one by one for the 3 columns, or you can look through the list, and I'll give you some time to work on it. And like before, when you're done, and if you want to, you can share your code in the chat window.
That was fast. We have an answer already.
Yeah. It looks like this is a pie chart. Yeah, it's great that you created pie charts. The exercise was about creating a bar graph, but of course, you know, you can create pie charts too. That's useful in different ways. You can see the proportion of different categories. Thanks, Rebecca. So it looks like some people are using a for loop. Some people are creating a chart individually for the 3 columns. I think 3 is a number that you can go either way. 4, it's not too many to do individually. Okay, so again, there are multiple ways to do this, but I'm using the same way that I did before. I'm using a for loop and using grouping by, I'm actually using a size to frame here instead of value counts, but you can create a data frame that way too. But whatever way you used, you should see charts like this. So for the address type, you should see block having the highest frequency, followed by intersection. And for the junction type, mid block should have the highest frequency. So you can see that these two graphs share similar information. And then if you look at the road condition, you should see that dry condition has the highest frequency. So, so far, we found that many accidents happened in daylight, in clear weather, mid-block rather than an intersection on a dry road. And this might all just mean that when the weather is nice and when it's light out, people travel more, and maybe that's why there are more accidents. We'll need to do more analysis to find whether or not darkness or bad weather might be a risk factor for accidents. So the next question I have is, can we predict severity of the accident from junction type? So I created this bar chart by first creating a pivot table by using junction type and severity code. And then I combined information from the two columns. And you can see that a lot of accidents happened in mid-block, like we saw earlier. But what's interesting about this graph is that a lot of these accidents resulted in property damage only and a little bit of injuries. Whereas when we look at this bar for intersection-related accidents, a large portion of the accidents only resulted in property damage, but then a bigger portion here compared to mid-block accidents involved injuries as well. So this suggests that when an accident happens at an intersection, the accident might be more severe than an accident that happened mid-block. Yeah, I think that's what Jenny's saying. Yeah. Okay. All right. So the last goal that I wanted to look at is just to look at the change in the number of accidents over time. And next week, if you are planning to attend the workshop on time series, you will get to see the change over time more closely. But I'm first looking at the change in the total number of accidents for all the locations. And let's see, I'm first creating a data frame here. And then, like Erin did, I'm dropping 2022 because data is still coming in. And so you can see that from 2006 to 2010, there was a decline. And then it increased a little bit towards 2016, and then it went down again towards 2018. So does anyone have any thoughts on why we might see these increase or decrease in the number of accidents? And I just want to hear your thoughts. I don't have information about why these changes happen.
I wonder if maybe there's a correlation with any construction projects?
Yeah, construction might be a factor, yeah.
Population change. I heard that, I'm new to Seattle, but I heard that it's changing a lot recently.
Yeah, yeah, if the number of people increases, accidents might increase too. Anything else? Interesting. Then you said that there was a big fine. I see. In 2017, I see. Yeah, so we need different data set or different information to figure out why we might see these changes over time. So we just looked at the change. Oh yeah, someone knows that if you have been living in Seattle longer, you know, yeah, you know what has happened in Seattle. I'm kind of new to Seattle, so I don't have a lot of knowledge about what has been happening in Seattle. So this is the change over time across the city. And I wanted to look at the change over time in the locations that we identified earlier as dangerous locations. So that's what I'm doing here. I'm extracting the data for those locations from the original data set here. And then just creating a similar line plot. So consistent with the overall change over time, you can see a downward trend from 2004 to 2018. But I noticed that after 2018, the green line is going up a little bit. So that's Aurora Avenue between North 117th Place and North 125th. And then this purple line is going down. That's Battery Street, Tunnel southbound between Aurora Avenue North and Alaskan Way, Viaduct southbound. So does anyone happen to know what happened in these two particular locations or any other location? What happened with their data collection? Yeah. So I think Erin said that this purple line, this location was closed after 2018. So that might be why the number of accidents went down. So that's all I have for section 8. Does anyone have any question before I hand it over to Erin again? Oh, I forgot to mention, but we are planning to have a Q&A section after Erin finishes her last section. Okay, Erin, go ahead, you can share your screen now. Oh, I should stop.
Okay. Here's hoping the internet connection holds. If I have lost audio, like I seem to be, talking and somebody else is trying to speak, please feel free to put something in the chat box and I will stop talking. So So starting with section 9, there are some simple scatter plots that I find personally is best for looking for outliers. I'm usually okay looking at tables, but nothing beats a simple scatter plot for identifying something that's weird. In this particular case, simple example, I'm looking at this particular incident here, where there are a lot of people involved based on that plot. I'm not exactly sure, because of the way that I structured this, that we're talking about the same event. And the way that this is structured, I'm not seeing every single incident from every year. I'm not 100% sure. I meant to research this. I don't think I'm getting an average. I think that the dots are just on top of each other. That's my supposition here. Because the scatter plot, I didn't select an average by any means. But obviously, each collision, there's only a few different options, right? Either there's no vehicles, which means it's pedestrian versus cycle, probably. Interesting to ask whether or not a motorcycle is classified in this data set as a vehicle or not. Certainly a bicycle would not be. But the vehicle counts go from 0 to 15. And the maximum number of fatalities, according to this plot, is just 5, which I'm not 100% sure that's true based on what we saw in an earlier plot, but I'm going to let you puzzle over that because I have more interesting plots to come. This is just showing matplotlib versus Seaborn. And this particular parameter is the old school parameter for color, which is not terribly useful in this particular instance. But I thought, what the heck, I'll include it just for a little bit of extra information. A much prettier plot here is the total injuries per collision over the years. In this particular case, I had to add the injuries, the serious injuries, and the fatalities. And if you remember, you have an excellent memory, far superior to my own, at the top when we told you a little bit about the columns. Serious injuries means like broken bones, means a problem that is more than like a scrape or a cut. Scrapes and cuts fall into injuries. Fatalities include not just somebody who died immediately at the scene, but up to 30 days later, assuming the injuries clearly resulted from the collision. So once we add all that up, if we're just interested in injuries and we're not interested in parsing out the particular type of injury, which is particularly useful because the amount of data in total that has injuries is far less, right? The vast majority of collisions do not result in any injury, or at least no injury that's immediately apparent to the law enforcement officer at the scene who's writing this information down in his or her report. The most common injury is whiplash, and that is not always immediately apparent at the time. You might just feel like a passing soreness, but it might be like a day or two later where all of a sudden you can barely move your neck. The interesting point here is talking about the outlier here. And I think that this corresponds, based on the earlier plots, to an incident that happened where there were 93 people involved in the collision. But at the same time, there were only 5 vehicles, a much smaller number of vehicles than people, which leads me to believe, also based on another look that I took, that it happened in September. So it was probably a school bus, I'm thinking, or a bus that was transporting college kids. So if memory serves, there was a Greyhound bus that involved a bunch of kids going to a game, I think. And there were quite a few injuries because oftentimes buses don't have seatbelts. So it's a good thing that we didn't delete those outliers earlier, because that is kind of a useful piece of information. Obviously, it's a collision that's not commonly repeated, so query as to whether or not you want to incorporate that and any suggestions to the city for improving traffic safety in general. However, recognizing the occasion in which a bus might be involved and therefore dramatically making the collision much, much worse is always something that I assume traffic planning folks keep in mind. So in this case, it's a little bit difficult probably for you to see. In a perfect world, a legend like this is better suited to a smaller number of categories, so the color variation is clearer. I mean, can you really tell whether or not it's 6 or 7 or 8? Probably not. This just, again, is the exploratory stage, the initial pass where we're looking at it. And we can dive in further to parse things a little bit more finely. For fun, I don't know about you, but in my mind, I often think that driving under the influence of alcohol or drugs tends to result in more collisions. I mean, if you're impaired, you're less likely to stop in time, you're less likely to handle a wet road. And so I thought I would take a look at under the influence versus not under the influence. And the immediate thing that you can tell is because this is normalized for the year, and because the vast majority of collisions, once again, have no injuries, that's why this looks funny. If you average a few large numbers with a whole bunch of zeros, you get really small values. But it is interesting to see that the collisions where there were no drugs or alcohol involved, at least as far as we know, as far as the data reflects, results in far, far fewer injuries. We could dive a little bit deeper and look at whether or not it's mostly the driver who's under the influence who tends to inflate the injury number, or whether or not somebody who's under the influence might be more likely to have people in their car, a party car, if you will. But that's just a quick look. And so we can see how much variation there really is in the course of, for instance, 2016 apparently was a pretty good year for people driving under the influence, since there were far fewer injuries that resulted, but this is the variance. And yes, what I happen to know, I don't know that this is necessarily related, but might be causally related, is that over the last 20 years, 15, 20 years, law enforcement has created a special task force called Target Zero, where they put additional troopers out and additional law enforcement officers who are specifically looking for people who are under the influence. And so there's a whole bunch of signs that remind people what the cutoff is, 0.08, and remind people there was a huge ad campaign. And of course, the most important in my mind, although we don't have the data to support that yet, this is something we have to further investigate. The biggest thing that changed in this time period is Uber and Lyft, right? If you make it easier for people who are drunk to get a ride, they're less likely to get behind the wheel, right? Tables have their place, right? I mean, when you're looking for something simple, the pandas crosstab function is very useful if you're just getting a quick snapshot, trying to figure out what the relationship is between two variables. In this case, I was kind of curious as to what kind of severe accidents tend to happen. I mean, I'm guessing, going into this, although it's nice to see that my intuition was borne out, that there weren't a lot of serious collisions happening in alleys. When the average speed is, 10, 15 miles per hour, not a lot of people are being injured in those collisions, fortunately. Intersections tend to be problems, but of course, block, I imagine, is kind of the all-purpose word. Basically, if it's not an intersection or an alley, apparently it got labeled as a block. But we'd have to look a little bit more into the data collection methods. That should just be like a running statement, right, on every single one of these things. But it depends on how the data was collected. Similarly, the severity of the collision with road conditions. You might think that ice and snow might have been a big factor, but it turns out, as you might imagine upon second thought, that we don't have a lot of snow and ice around here. On those days, certainly the rate of collision almost certainly increases, but there aren't that many of those days. So the winner for the number of serious collisions is in wet weather. Since we did want to leave some time for questions, I'm going to bypass the chi-squared test. Yes, I think that I read, and this is a little bit old, so I guess I gotta say this with a grain of salt. Most collisions happen in parking lots. Parking lots are the #1 location for collisions. Obviously, they're low speeds, not a lot of injuries happening, but there's a lot of people moving in and out, failing to look behind them. Circumstances change, lots of pedestrians walking around. This is, I'm all about the color, right? So I'm all about the prettier plots. I find heat maps to be useful. This is maybe not my very best one, but in terms of looking for interesting relationships between variables, some things that immediately need further investigation is, for instance, the year seems to be very strongly related with this, and this is a designator for, I'm not going to scroll all the way up to make everybody dizzy, but if you want to scroll all the way up on your own individual one, I think that this describes the nature of the collision, like whether or not you're turning onto a left, making a left turn onto a one-way. I think that's what that referenced. But why is that so highly correlated with year? I don't know. Further investigation is necessary. You would expect that, generally speaking, if you have more vehicles involved, there are more people involved, right? So it seems pretty reasonable. If you're at a crosswalk, then you're more likely to have pedestrians involved. This is a less pretty, but also just a quick way to know what's important. You can set this threshold by whatever the criteria is that you deem to be important. In this particular data set, there's not a whole lot of correlation, which is why I set my criteria very, very low at a measly 10%. But you see some minor, technically, if correlation is this low, it's hardly considered correlation, right? But well, see prior caveat, further investigation is necessary. This is more of a classic correlation. I narrowed down the categories just to the numeric values to compare. Interestingly, well, it's a weak negative correlation, but the more vehicles involved, apparently the fewer pedestrians, or vice versa. I guess maybe that makes sense. If a vehicle hits a pedestrian, there's not usually a whole bunch of other vehicles also involved in that collision. Although, if you stop short and a whole bunch of other people rear end you, they're involved in that collision. And this is just a little extra snippet for the newer folks. If you have an amazing plot that you spend a lot of time cultivating and you want to save it, you can just add the name, whatever name you want, and you can change. There's a whole bunch of different parameters you can set. I think you can also save it as a JPEG, I think. Sometimes JPEGs act weird with pandas, but I think JPEG will also work. And this will save the file, the plot. Okay, I think I'm going to hand it back to Niwako.